Good morning. Welcome to Krishna's class. We were proving the existence of Lebesgue measure on RK. We resorted to the route of doing this by applying the Rees representation theorem. And in this process, we had to construct a linear function on CC RK. So we have, this is the situation, x is equal to RK. RK has all the properties, namely it is a locally compact sigma finite Hausdorff space. Now let us take CC. This consists of all continuous functions with compact support on RK. We'll take real value functions. And we take, let lambda be a positive linear function on RK. Then there exists a complete regular measure M. Now this is what we have from the Rees representation theorem, and its further consequences of properties like sigma finite and so on, which we have proved. Now our claim is that this is, we claim that the lambda we have constructed gives rise to Lebesgue measure. So this is the situation that we have. So what was the lambda we have constructed? Recall that lambda f lambda nf okay, where lambda nf equal to 2 to the power minus nk summation over x belonging to Pn for x n equal to 1. Now for n equal to 1, lambda turns out to be the Riemann integral. So for higher values of k, we do not know yet. Now for k, we define lambda n as given above. Which is an approximation to f through what are called step functions. Functions which are constant functions on hypercubes. Okay, with the corner points as elements of Pn. So this is what we have. Then we proved that Rk, this is with compact support, and which is a positive linear functional on CCRK. Therefore, it determines a say M is a measure such that FTM. This is simply the application of the series representation. Okay. Now, what we are worried about or what we want to establish is that this is indeed the Lebesgue measure. So, we claim what do we mean by that? This means M satisfies certain properties. The Lebesgue measure on RK on R obtained on this means M satisfies the following properties. It's not any positive measure, but a measure with certain specific properties, which is the characteristic feature of Lebesgue measure on R. Okay, so let us explore that. So, what does this mean? This means we have the following. It satisfies certain specific conditions. One is a moral, which means the all moral sets are measurable, that is, they belong to the second property is for cases the measure of cases E measure of E is equal to volume of which we have defined. This is for cases. 3 M is translation unit. That is, for every E belonging to strip them, and x belonging to Rk, that is M is translation invariant. 4 is complete and regular. So these are the important properties. Then find for any t from okay, t is t linear, measure of t of t is a measurable subset is equal to some delta t, the scalar multiplied by measure of t for every. Now this delta t depends on what the linear transformation is. It does not depend on t actually. Okay, that's important. So when t is rotation, delta t equal to now these are the important properties that we have to verify, and then we'll go on. I think I have listed out all the properties, and there may be one or two small things which are missing, but I will just take it up. So let us start proving this now. As we have remarked earlier, that for k equal to 1, lambda f is the Riemann integral of the Riemann integral of f. That is This is true for every belonging to CCX. So now let us start proving these results one by one. Now let us first observe P that we have stated in the theorem. First we make a statement about P as in the theorem. Now lambda, this corresponds. This is the measure space on RK. So they are uniquely determined and so on. Then M is a complete measure. So that comes out straight away from the theorem that we have proved earlier. Since RK is sigma compact, M is regular. So this is important. Okay. So if the sigma compactness is not there, we cannot say that M is a regular measure. But now it is a regular measure as we have defined earlier. So please look into the definition of the regular measure. So B actually in the part B in our theorem, the B statement of the theorem actually follows. It's a direct consequence of the Trees representation theorem. So now let us slowly start verifying all the other parts. So that means we have to verify A, we have to verify C, D, E. There are 4 parts to be verified. So what is the statement of A? A. Where W is a yes. And what we have is, we shall write W is, okay, W we write as open case. W equal to X such that beta I for 1 less than or equal to I, where of course X is equal to, these are the variables or the components of vector X, which turns out to be the variable here. So this is essentially equal to the product of the open intervals these are open intervals. Okay, so that is your W. Then prove that then we have the following, namely volume of W equal to theta I minus alpha. Okay, now what we claim is measure of equal to this is the thing that we shall prove this. So let ER be the union of those boxes we have defined omega R disclosure lie in W. What we mean by that? We have the K boxes whose corners are points in PR. That is what this boxes in omega R. Okay. PR consists of all integral multiples. PR consists of all integral multiples of 2 to the power minus RK. Okay, so that is what we have defined earlier. So just look into it. That means you have boxes with corners having coordinates which are multiples of 2 to the power minus okay, the coordinates are multiples of 2 to the power minus r. So if they are in Rk, there are k components for this. Each one is an integral multiple of root power minus r. That is what it means. Okay. Now we choose functions fr so that ER closure is subordinate to FR is subordinate to W. Now you see that ER is contained in W, which is a union of boxes. Okay. Now what you do is you take the ER closure. ER closure is compact. Therefore, you see that you have this property. This is contained. Now what do? You take functions fr with the property that, what are the property? Fr is equal to 1 on ER closure. Okay. And support of fr is contained in W. That is, this is a function compact support. Fr these are the properties then for Fr. What is meant by that? Okay. Put GR equal to maximum of so corresponding to R equal to 1 you have an F1, R equal to 2 you have an F2, etc. R equal to for R, see, you have F1. So these finite number of functions you take, and the maximum of these functions you take as GR. Okay. In our construction of lambda shows that volume of ER, look at the definition of ER, is less than or equal to lambda of FR is less than or equal to, because GR is the maximum of F1 up to FR, this is equal to lambda of GR, which is less than or equal to or volume of W. That's clear. Okay. So this inequality is clear because FR is equal to 1 on ER closure. Okay, right? And support of FR is contained in W. And because of this choice, you have lambda GR is less than or equal to volume of. Okay. Now, as R tends to infinity, volume of ER volume of W. Because ER is approximating W from within using this compact sets ER. I mean, you see that ERs are sort of disjoint sets that you construct, and you see it's contained in W, properly contained in W. But as R tends to infinity, you see that this is going to cover the whole of R. Essentially, the idea is you in R2, see, you have you are looking for full squares. Bigger one, say this is E1. Okay, then you have E2, etc., etc. E2 will be, you subdivide this and take the full squares inside that and so on, and then put the union of that, that's equal to E. So this is how the construction goes, and therefore you see that the total volume of ERs, okay, or volume of ER, the as R tends to infinity, becomes volume of W from within. Okay. Which goes to the measure of W. Because GR tends to identically equal to 1 on W. That is because theorem, and the fact that GR this actually tends to 1. Okay. So that means this function actually goes to the characteristic function of W, and therefore the integral becomes equal to the volume of ER is equal to volume of W, and volume of ER converges to, say, actually measure of W. Therefore, you see, measure of W is equal to so that is the first statement that we have proved, namely A. Now we have to, this is for W. Now we have to do this for all right, for all cases. Since K7 is the intersection of a decreasing sequence of open cases that's how you do it. Okay, so that completes the proof of A. Now we need to prove the other statements. I think we will stop it here today and then take up the proof of in the next lecture. So I think I'll stop here for today and then continue with it. Possibly, most probably. Thank you very much.